Now, these four vectors that we've written in index notation, v mu, these are called contravariant four vectors. That is, if I know the vector v mu in one reference frame, or say in the frame of an observer S, and I want to find v prime mu in the frame S prime, then the transformation rule is v prime mu is lambda mu nu v nu, where I've summed over nu. Okay, this would relate the vector in S prime to the vector in S. Okay, and in the special case, for example, where S prime is is a frame which is moving along the x direction with the velocity v, the matrix lambda is gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. Okay, so in particular, if I take lambda 0 0, this is gamma, lambda 0 1 would be minus gamma beta, and so on. Okay. And if v were the standard space-time vector, v0 would be ct, v1 would be x, v2 would be y, and v3 would be z. Okay. So this defines the our transformation rules for four vectors. Now, any collection of four numbers obviously does not form a four vector, but I could imagine taking other combinations of these four quantities. And since I know how v0, v1, v2, v3 transform, I would also know how those other combinations transform. So let me construct something here. I'm going to construct a new kind of four vector, which is really constructed from the old four vector with components v0, v1, v2, and v3. Okay, so the way we're going to construct this four vector is we're going to take v mu and we're going to multiply it by the matrix G. Okay, so we're going to take a G dot V. Okay, and we're going to ask, what is this quantity? And let's call this some new quantity. This is still in the frame S. Okay, so everything that we're constructing now, both sides of this equation, this is in frame S. We're not making a Lorentz transformation. We're just asking what this quantity is. So this is also in a new object, which we'll call, let's call it W. This is also in frame S. Okay. So in index notation, V has an upper index, G has lowered indices, and we are summing the raised and lowered indices. So the object W would have a lowered index in this case. Okay, so explicitly the entries of G, so G is this matrix with zeros everywhere else. So G00 is 1, G11 is minus 1, G22 is minus 1, G33 is minus 1, and all other entries of G are 0. So what this is going to do is, supposing I have V0, V1, V2, V3, the components of W for each value of nu would be W0 would be V0, W1 would be minus V1, W2 would be minus V2, and W3 would be minus V3. Okay. So it's not that I've constructed a new four vector, it's just that I've taken the components of the old four vector and performed an operation on them. Okay. And I'm still talking about the same four vector, but I've just redefined the components of that 4 vector. Now, the transformation law for W is obviously going to be different from the transformation law for V. All right. So let's ask, what is the transformation law for W? So now suppose we go to a frame S prime. We'd like to know what is W prime. Okay. And we know what V prime is. And we know what G will be in the new frame. Okay, so this is known, this is known. The metric G is unchanged, okay, because the space-time interval is unchanged. So the metric G is unchanged in a new reference frame. We know how V prime transforms, and therefore we can derive how W prime would transform. So we had W nu is G nu mu V mu. So now if we make a transformation, let's transform both G and V. Okay. So in matrix notation, V would become lambda V and G would just become G. And this would give us our W prime. In index notation, we would write this as G again with lowered indices, nu mu. This is W prime nu. And lambda V would be lambda mu alpha V alpha. Okay. Note again how the raised and lowered indices, repeated indices, are summed over. Okay. So you see that the transformation rule for W looks like this, but we want to write the transformation rule for W not in terms of V, but in terms of the original W. But that's easy to do. Again, if we look at this equation in matrix form, okay, what we can do is we can write this as W prime is equal to, let's stick in factors of lambda transpose and lambda transpose inverse. So this is the identity matrix dot G dot lambda dot V. And now, since matrix multiplication is associative, we can perform this matrix multiplication first. And by the defining property of the Lorentz transformations, this is just G, so I can write this as G times V. And so now we have lambda transpose inverse times GV, which we can write as W. Okay, so the transformation law for W is different from the transformation law for V. Okay, it's not through the matrix lambda, but rather through lambda transpose inverse. And in index notation, we could write this as W prime nu is lambda transpose inverse, whatever this matrix is, we take the nth component and the mu component, W mu. Okay, so this is the law in index notation for the transformation of W. This law is not an independent law, it just comes out from the law of transformation of our regular contravariant 4 vectors. Okay, so you don't have to look at the transformation law for these 4 components if you don't want to. Most of the time you just need to look at contravariant 4 vectors. But sometimes it's useful to write down the product of G with a contravariant 4 vector and define that as what is called a covariant 4 vector. That is these W's with lowered indices. Okay. So let me show you an example of where this is useful. So consider two contravariant 4 vectors, b mu, let's call it a mu and b mu. And let's consider the dot product of these two 4 vectors. So the dot product is a Lorentz invariant quantity. So let's write down this dot product. So the dot product is A transpose dot G dot B in matrix notation. So this is A dot B is this. And in index notation, we'd write this as A mu G mu nu B nu. Okay, again, the index mu is summed over and nu is summed over. Okay. Now, if you look at this quantity is exactly what we called, we can define a covariant 4 vector, which we write as C mu, which is G mu nu B nu. Okay, which is, so that we can write this as A mu C mu. So the dot product of A and B is related to a simple product between A, which is a contravariant 4 vector, and mu and C mu, which is a covariant 4 vector, which is derived from B. Okay, so when taking these dot products, sometimes it's convenient to switch from contravariant 4 vectors to covariant 4 vectors in such a way that you can write this dot product very simply without explicitly writing the matrix G. One other thing that I'd like to point out is typically when you go from the contravariant 4 vector to a corresponding covariant 4 vector, you typically do not change the letter that describes this contravariant 4 vector. So conventionally what you would do is, if I write down b mu, this with a lowered index, this is related to b mu with an upper index through this transformation. Okay, so this is the corresponding covariant 4 vector that corresponds to this contravariant 4 vector. And so the dot product of A and B is just written as A mu B mu, which you can also show can be written as A lower mu B upper mu. Okay, where this is the covariant 4 vector corresponding to the contravariant 4 vector A mu, and B mu is the contravariant 4 vector corresponding to this covariant 4 vector B mu. Okay. There's a one-to-one correspondence between the covariant 4 vectors and their contravariant 4 vectors. They're just related through the metric G. Okay, so to be concrete, let's take A to be CT X, Y, Z. And let's consider A dot product with A. So A dot product with A is A transpose dot G dot A, which you can write as CT square minus X square minus Y square minus Z square. This is the space-time interval. But you could have also written this in terms of A mu, where A mu upper is CT. I can think of it as this column vector, and A mu lower I can think of as, actually let me just write it this way. It doesn't really matter how I choose to write it, but let me write it as A lower mu, A upper mu. And A mu we can write as CT X, Y, Z, and A lower mu we can write as CT minus X minus y minus z. And it's easy to see what the dot product is. The dot product is then just multiplying this row vector with this column vector. Okay. And this row vector was constructed from the column vector by multiplying the column vector by G, where G is the matrix with zeros everywhere else. Okay. So in this way, we see that the index notation is really quite convenient when we talk about dot products. Now, this seems like overkill when you have only one index, but the next thing that we'll do is we'll talk about tensors, which are objects which have multiple indices. And there we'll see that the use of covariant and contravariant notation is actually extremely useful.